No one has ever seen a black hole up close. No one knows if wormholes really exist. Gravitational waves are much too faint to be detected without incredibly sensitive instruments. The bending of space, the slowing of time, it's all way too complicated and way beyond our daily experience. To really understand these things, you need to master Albert Einstein's theory of general relativity. There's a famous anecdote about an English astronomer, Arthur Stanley Eddington. In the early 20th century, Eddington was one of the biggest popularizers of Einstein's new theory of spacetime. After a public lecture, a person in the audience asked him, "Professor Eddington, is it true that there are only 3 people in the world who really understand general relativity?" Eddington thought for a while, then replied, "Who might possibly be the third?" Well, it's not that hard, of course. Tens of thousands of theoretical physicists all over the world understand the fundamentals of general relativity. Then again, new theoretical insights keep popping up all the time, especially in the realm of black holes, where quantum effects become important. There's Stephen Hawking's theory of evaporating black holes, Kip Thorne's wormhole shortcuts, Gerard et Hoof's holographic principle, and Leonard Suskind's firewall. I'm not going into details here, but if the greatest minds alive keep finding new and surprising insights and keep arguing about them, it's clear that the full scope of general relativity is still beyond their grasp. The examples given here are just a few of the less far-fetched ideas. The journal Physical Review Letters also runs papers on 11-dimensional spacetime, time travel, and the multiverse. And you thought Interstellar was speculative? Maybe this is why so many people are interested in this stuff, even though it might appear to be rather useless knowledge. You don't need to know about black holes to run for president, and gravitational waves are not going to solve the problem of global warming. We can live out our lives without a care for general relativity. Still, it's exciting and intriguing, and it surely fires the imagination. Maybe that's reason enough. Moreover, general relativity tells us about the way the world works at its most fundamental level. And isn't the quest to really understand our world one of the things that sets us apart from other animals? To be honest, we weren't very good at understanding our world for many thousands of years. The first agricultural societies arose some 12,000 years ago in the Middle East. Back then, people were well aware of the cyclical motions of the sun and the moon. They saw patterns in the stars. They even noticed a handful of bright stars slowly wandering across the constellations. But that was about it. They had no clue as to the true nature of the celestial bodies. No urge to know even. Sun, moon, and planets were seen as gods, above and beyond our everyday world. Nothing much changed until the time of the great Greek philosophers some 2,500 years ago. That's 9,500 years, many hundreds of generations, without significant progress. If we compress 12,000 years of history into a single 24-hour day, starting at midnight, we're already past 7 p.m. by the time Aristotle proposes the first model of the universe, consisting of nested crystal spheres. Our ancestors had the brainpower. After all, they were Homo sapiens just like us. They just didn't care enough. The Greeks did care. They correctly inferred that the Earth is a sphere. They even determined its circumference with surprising accuracy. Some school books still would have you believe that Christopher Columbus was the first person to discover the true shape of the Earth, but that's plain wrong. And even though the Greeks didn't know what the sun, the moon, the planets, or the stars were, at least they tried to understand their intricate motions. As the name implies, Ptolemy's model had the Earth in the center. The sun, moon, and planets circled around the Earth in a complicated assembly of primary and secondary orbits. Ptolemy's worldview even explained why the planets appear to be moving backward every now and then. It took ages before people realized that something was amiss. That didn't happen until Polish astronomer Nicholas Copernicus published his heliocentric worldview, centered on the Sun instead of the Earth, in 1543, just past 11 p.m. on our condensed timeline. Understanding our world was a frustratingly slow process for most of the past 12,000 years. Soon after Copernicus, however, the rate accelerated. Scientists discovered that the book of nature is written in the language of mathematics, as Italian physicist Galileo Galilei so nicely put it. Galileo studied how stuff moves. He proved Aristotle wrong on a number of his assumptions, and he used mathematical equations to describe his findings. Not much later, in Germany, Johannes Kepler formulated his famous laws of planetary motion. What does this history have to do with black holes, gravitational waves, and the secrets of space-time? Everything. Copernicus, Galileo, and Kepler laid the groundwork for Isaac Newton's theory of universal gravitation, first published in 1687. And Albert Einstein's general relativity, the theory behind interstellar, replaced the old ideas of Newton. Our understanding of the world is made possible only by improving on the work of others. The crystal spheres of Aristotle and the wormholes of Kip Thorne are connected by one great arc of clever thinking and discovery. Another revolution occurred in the early 17th century, a revolution of tools. Dutch spectacle maker Hans Lippershey invented the telescope, but the use of the new instrument was subsequently pioneered by Galileo. Galileo discovered craters and mountains on the Moon, dark spots on the Sun, satellites orbiting Jupiter, and countless stars in the Milky Way. Eventually, ever larger telescopes brought us binary stars, asteroids, nebulae, and galaxies, and black holes, of course. Without the telescope, astronomy would still be in its infancy. Let's do a quick virtual tour of the cosmos to make sure we have the general picture right. Earth is a planet. Like 7 other planets, it orbits the Sun. The 4 innermost planets, Mercury, Venus, Earth, and Mars, are really small. They consist of metals and rocks. The outer 4, Jupiter, Saturn, Uranus, and Neptune, are much bigger. They mainly consist of gas and ice. Between the orbits of Mars and Jupiter is a belt of asteroids, rocky leftovers from the birth of the solar system. Beyond Neptune, there's another debris belt of ice balls and frozen dwarf planets, of which Pluto is the largest. Look up during the daytime and you'll see a huge sphere of incandescent gas in the sky, the Sun. The planets in the solar system receive all their light and heat from the Sun. Look up at night and you'll see thousands of other suns, the stars. They appear small, faint, and cold, but that's just because they are tremendously far away. Put the Sun at a similar distance, and all you'd see is yet another small pinprick of light. Remember that every star is a sun, and that most of them are likely to be accompanied by their own family of planets. In fact, at the time of writing, well over 3,000 exoplanets have been discovered. Too bad we can't go there and take a look, at least not in the foreseeable future. Even light, traveling at 300,000 kilometers per second, would take 4.3 years to travel from the Sun to the nearest star, Proxima Centauri. That's why astronomers say that Proxima is at a distance of 4.3 light years. That's almost 9.5 trillion kilometers. Have you ever tried to count the stars in the night sky? With the naked eye, you can see a few thousand of them, depending on how dark your sky is. Most of them are a few tens or a few hundreds of light years away, which is incredibly distant for most human beings, but relatively close for astronomers, our cosmic backyard. The vast majority of stars in our Milky Way galaxy are much further away. To see them, you'll have to use a telescope. They come in many colors and sizes, and their names, red dwarfs, white dwarfs, yellow subgiants, blue supergiants, evoke the inhabitants of a fairy forest. And there are many of them. Astronomers now think that the Milky Way contains several 100 billion stars. One of them is our Sun. We're not done yet. Our Milky Way galaxy is not alone. The universe is filled with other galaxies. Grand, majestic spirals like the Milky Way and Andromeda, huge elliptical collections of old stars, small, irregular dwarf galaxies. There's an overwhelming variety, and an overwhelmingly large number too, spread out over a volume that is many billions of light years across. In December 1995, for the first time, astronomers trained the Hubble Space Telescope on a tiny, seemingly empty patch of sky. They left the camera shutters open for 10 days straight. The result was a breathtaking photo of more than 1,000 faint, distant galaxies in an area that would disappear behind the head of a pin held at arm's length. One pinhead's diameter to the left or to the right would reveal another 1,000 distant galaxies. So here's the current view of the observable universe. It's vast, dark, cold, and empty. But sprinkled throughout the void are about 2 trillion galaxies, grouped in clumps and clusters. Are you far out in space and want to find your way home? Better buy yourself an incredibly accurate navigation system. There are no road signs along the cosmic highways. Finding the proverbial needle in the haystack is a lot easier. If you succeed in locating the Milky Way galaxy, pause for a second to take in the view. A few 100 billion suns are arranged in beautiful spiral arms amid stellar clusters, bright nebulae, and dark dust clouds. And just one of them, a rather inconspicuous middle-of-the-road star, is our Sun. It lives out its life in one of the Milky Way's quiet suburbs, at the inner edge of a spiral arm where nothing much happens most of the time. Orbiting that tiny beacon are 8 minuscule planets. One of the smaller 4 is Earth. On this mote of dust, over just a few recent centuries, human beings are beginning to unravel the mysteries of the universe. Well, at least we're trying. It's a humbling thought. Homo sapiens is almost impossible to find in the vastness of space. We are also newcomers on the cosmic stage. Here's a revealing metaphor. Suppose all of the history of the universe was recorded in a 14-volume encyclopedia. 14 fat tomes, 1,000 pages each in fine print. The Big Bang would be on the first line of the first page of Volume 1. The first stars and galaxies would form somewhere halfway through Volume 1. But the birth of the Sun and the planets is described only in Volume 10. The dinosaurs go extinct on page 935 in Volume 14. Homo sapiens appears on the bottom fifth of page 1000. All of our written history would be crammed in the second half of the very last line. The astronomical view is one way to understand our world. Many physicists would use a different approach. Rather than simply describe everything you see, galaxies, stars, planets, find out what everything is made of and how it all works. Suppose an astronomer and a physicist both study J.R.R. Tolkien's The Lord of the Rings. The astronomer presenting her findings would describe the trilogy's storyline, the protagonists, the metaphorical meaning, the writing style, and so on. The physicist would describe the alphabet, letter frequencies, rules of punctuation, and grammar. But aren't these the same for many widely differing books? Yes, the physicist would exclaim enthusiastically. That's the great thing about this approach. You can stop focusing on the peculiarities and start finding the common fundamentals in order to develop the deepest possible understanding. Of course, both approaches have their pros and cons. They're really very complementary. So, just as every possible book is composed of a small number of different letters and has to abide by the rules of grammar, all objects in the universe are composed of just a small number of elementary particles that interact through the fundamental forces of nature. The surprising thing is that the world around you, pinheads, people, planets, and protoclusters, is composed of just 3 types of elementary particle: the up quark, the down quark, and the electron. And just as letters can be grouped into words, sentences, paragraphs, and books, Those three particles can make up atoms, molecules, compounds, and literally every object you can think of. As for the fundamental forces of nature, physicists know of only four. Two of them act at very short range. They play a role only at the scale of an atomic nucleus. That's why they're called the strong and the weak nuclear force. The other two, electromagnetism and gravity, can be experienced in the world at large, as everyone knows who has switched on a light bulb or dropped a wine glass. I'm leaving out lots and lots of details here. Neutrinos, unstable elementary particles, antimatter, force-carrying particles, the famous Higgs boson, dark matter, supersymmetric particles, tetraquarks, a possible fifth force. The list goes on and on. One particular detail is important to our story about space-time and gravitational waves: the weirdness of gravity. We're all quite familiar with its obvious effects, but somehow gravity behaves very differently from the other fundamental forces of nature. According to Albert Einstein, that's because gravity is intimately connected to space and time. Now, try to explain that to Isaac Newton. Newton never knew the true nature of gravity, of course. He just derived a universal formula that usefully described the attractive force between two masses at a certain distance from each other. But like most of his contemporaries, Newton considered space and time to be independent, absolute concepts. In fact, Newton's views on space and time are much like our own intuitive ideas. Space is simply there, a three-dimensional nothingness that goes on forever. An object, like an elementary particle or a planet, can sit at a certain location in space, or it can move from one location to the next. If we choose a particular reference point, all other locations can be identified by just three coordinates. Starting at your reference point, the three numbers tell you how far you have to go forward or backward, left or right, and up or down to reach the other location. Space is a bit like three-dimensional graph paper. It's the empty, unchangeable backdrop against which all events in the universe play themselves out. And time? The imaginary clock of nature ticks away the moments that make up a dull day as well as the seconds since the birth of the universe. Time is the absolute, infallible metronome of the cosmos, tagging each and every event with a unique timestamp. Oh, and it's one-dimensional. If you choose a reference moment, you need only one number to tell you at what time any other event takes place. I'm confident you have no trouble imagining space and time the way Newton did. It's the natural way to think of them. Our brains are wired to come up with this convenient view. Alas, it's wrong. What Einstein showed is that space and time are linked. Three-dimensional space and one-dimensional time are actually interwoven in four-dimensional space-time. Einstein also showed that space and time are not absolute, but relative. That's of course why his revolutionary theory is called the theory of relativity. What's the distance between 2 points in space? Depends on whom you ask. For someone traveling at half the speed of light, the distance between 2 points in space is much smaller than for someone at rest. At rest with respect to the 2 points, that is. The same is true with the time interval between two events. The faster you go, the slower your clock is ticking. The only thing that is absolute, the same for all observers independent of their motion, is the four-dimensional separation between two events, at two locations in spacetime. Finally, Einstein showed that mass, and energy too, exerts an influence on four-dimensional spacetime. Straight lines are slightly bent under the influence of massive objects such as stars or black holes. For smaller and lighter objects, asteroids or apples, the effect is completely negligible. The result? Anything that follows a straight line, like a ray of light or a planet, starts to move along a curved path in the presence of a massive body. What we perceive as gravity is really the effect of the curvature of space-time on the motions of other bodies. And since we're talking about the curvature of space-time, time is also influenced by the presence of massive bodies. Close to a black hole, your clock starts to tick slower and slower. If you think this all sounds crazy, go ask the fictional interstellar astronaut Joe Cooper. Together with his crewmates Amelia Brand and Doyle, he spends just a few hours on a world known as Miller's Planet, which orbits the giant black hole Gargantua. Because the planet orbits so close to the black hole, space-time is curved dramatically, and time there proceeds at a snail's pace. When Cooper, Brand, and Doyle return to Endurance, Nikolai Romilly, the fourth crew member, has aged 23 years. The strong space-time curvature is also evident in the appearance of Gargantua itself. The black hole is surrounded by a flat, equatorial disk of superheated gas from which matter falls into the hole. Normally, you would expect to see only the near side of the disk. After all, the far side is behind the black hole. But thanks to the curvature of space-time, light from the far side is bent all the way around Gargantua. As a result, the black hole appears to be surrounded by a bright ring. Kip Thorne's involvement must have been annoying to the visual effects artists and computer animators at Double Negative, the firm in London that had to turn his space-time equations into breathtaking footage. Sometimes the Caltech physicist wasn't allowed the last word, and scientific accuracy had to be compromised. As Thorne describes in his 2014 book, The Science of Interstellar, movie director Christopher Nolan didn't want to confuse his audience too much. But in the end, Thorne was extremely satisfied. "What a joy it was when I first saw these images," he writes. "For the first time ever in a Hollywood movie, a black hole and its disk depicted as we humans will really see them when we've mastered interstellar travel." So we can describe and visualize the effects of space-time curvature on the bending of light paths and the flow of time. But how should we imagine this fourth-dimensional construct, let alone its curvature? In 1917, Albert Einstein wrote a short book about his new theory, simply called Relativity, the Special and the General Theory. Later, others wrote about relativity too. One of the funniest is Mr. Tompkins in Wonderland, 1940, written by cosmologist George Gamow. The trick everyone uses to visualize four dimensions is quite straightforward. Forget about one of them. Of course, we don't want to ignore the time dimension, but it's okay to throw one space dimension overboard. That leaves us with two dimensions of space and one of time. As a result, space-time has become three-dimensional, something we're familiar with. In two-dimensional space, things can move only forward or backward and left or right. There's no up or down. So let's focus on motions that occur in two dimensions on a horizontal plane. I want you to visualize two things that travel through this plane in a straight line. One is a ray of starlight traveling at 300,000 kilometers per second. The other is a planet traveling in the same direction, but 10,000 times slower at a mere 30 kilometers per second. If there's no external influence on either of them, both will follow the same straight path, albeit at very different velocities. Let's now put the Sun in the same plane at some 150 million kilometers from the straight path. We know that the mass of the Sun creates a curvature in space-time. As a result, both the path of the light ray and the path of the planet are bent. But something strange is going on. The path of the light ray is bent by only a very small amount. But the path of the planet, let's call it Earth, is bent much more strongly, all the way into a circular orbit. What's happening? If both are influenced by the same curvature, wouldn't you expect both of them to follow the same curved path? No, you shouldn't. Here's the reason. We're talking about curved paths not in space, but in space-time. If we really want to understand what's going on, we should add the time dimension to our two-dimensional space and consider motion in three-dimensional space-time. Here, time has taken the place of the third space dimension, up-down. In fact, we've created a new three-dimensional coordinate system. The x-axis and the y-axis in the horizontal plane have tick marks every 300,000 kilometers, the distance light travels in 1 second. The vertical z-axis has similarly spaced tick marks every second. Let's look again at the light ray. At time 0, it is located at a certain point in space. 1 second later, it has traversed 300,000 space kilometers, 1 tick mark in the horizontal plane. But in three-dimensional space-time, it has also traveled 1 tick mark up. After all, 1 second has passed. So in space-time, the light ray moves along a path that is tilted at 45 degrees. Now let's examine Earth. In 1 second, it travels just 30 kilometers. It takes our planet 10,000 seconds to cover 300,000 space kilometers. That's 2 hours and almost 47 minutes. So the path of Earth in three-dimensional space-time, its world line, is much less tilted than the path of the light ray is, just 20 arcseconds or so. An arcsecond is 1/3600th of a degree. To a casual observer, the light ray obviously moves diagonally, while the planet moves nearly straight up, almost vertically. So far, so good. Now what happens if we add the sun to the picture? In our simplified story, the sun doesn't move in space. Its velocity is 0 kilometers per second. Consequently, it moves exactly vertically in three-dimensional space-time. But the sun's mass creates a tiny curvature in space-time. As a result, the world line of the light ray and the world line of the planet are both bent very, very slightly. Here's how. The diagonal world line of the light ray is slightly bent, but not for long because of its high velocity. In no time, the light ray has left the area where space-time is curved by the mass of the sun. As before, it travels along a straight space-time path at the same vertical tilt of 45 degrees, although the tilt is now in a slightly different direction. Projected back onto the plane of two-dimensional space, we see that the light ray's path has experienced a slight change of course. Earth, however, stays in the curved region. It keeps moving through space-time along an almost vertical path at the same angle of 20 arcseconds. But the direction of this small tilt is slowly changing all the time because of the curvature induced by the mass of the sun. After almost 8 million seconds, 3 months or so, the direction of tilt has changed by a full 90 degrees. Projected onto the plane of two-dimensional space, we see that the planet has completed 1/4 of an orbit around the sun. But that's not a strong curvature at all. In 8 million seconds, the planet has moved 8 million tick marks up through space-time. In the same time, it has traversed a mere 236 million space kilometers. That's less than 800 tick marks in the horizontal plane. It would be extremely hard to see the curvature of the planet's path in space-time by eye. It's still an almost perfect vertical line. After 1 year, Earth has completed a full orbit around the sun, corresponding to just over 940 million space kilometers. But it has taken 31.5 million seconds to do that. Earth's helical world line in space-time is almost indistinguishable from a straight line. That's because the sun is not extraordinarily massive, and the resulting curvature of space-time is small. Still, if we forget about the time dimension and look only in the plane of two-dimensional space, Earth's path is strongly curved, all the way into the familiar circular orbit. Our speeding light ray, meanwhile, has traveled almost 1/4 of the distance to the nearest star. This is all quite difficult to grasp if you are hearing about it for the first time, and I didn't even ask you to visualize 4-dimensional space-time. If you've lost track, you can always revisit this tomorrow morning or next week. In any case, you now understand why our everyday intuition lets us down if we want to understand the peculiarities of space-time and general relativity. And that's a good lesson. In dealing with colliding black holes, extremely strong space-time curvature and gravitational waves, we can't trust our gut feeling. Instead, we have to rely on supercomputer calculations based on Albert Einstein's theory of general relativity. If we trust Einstein, we'll have to accept the results of those calculations. This is one of the reasons why Kip Thorne was so happy with the Interstellar project. A visual effects company such as Double Negative has much more powerful computers at its disposal than a Caltech theoretical physicist does. The resulting movie sequences provide scientists like Thorne with new, valuable insights. As he writes in The Science of Interstellar, "For me, those film clips are like experimental data. They reveal things I never could have figured out on my own without those simulations." Now, what do scientists do when they gain new insights? Publish a paper, of course. That's just what Thorne did. 2 papers, actually. One on Interstellar's wormhole, the other on the movie's giant black hole, Gargantua. The first one, titled Visualizing Interstellar's Wormhole, was published in the prestigious American Journal of Physics. The other paper, Gravitational Lensing by Spinning Black Holes in Astrophysics, and in the movie Interstellar, appeared in another professional journal, Classical and Quantum Gravity. Both papers are co-authored by Oliver James, Eugenie von Tunzelmann, and Paul Franklin. James is chief scientist at Double Negative, von Tunzelmann is the company's computer graphics supervisor, and Franklin is Double Negative's co-founder and visual effects supervisor. It's nice for a theoretical physicist to be listed as an executive producer in the Internet Movie Database, IMDb, but it's equally nice for special effects experts to end up at archive.org, the largest electronic repository of physical science papers in the world. There was just one small disappointment that Thorne had to swallow. Originally, he had hoped that gravitational waves would be featured in Interstellar. After all, he was co-founder of the LIGO project, and for all he knew, the first direct detection of these elusive space-time ripples might occur in the same year the movie was released. Unfortunately, Christopher Nolan believed they would make the storyline way too complicated. In any case, the first detection of gravitational waves, GW150914, didn't occur until 323 days after the official release date of the movie.